Hello, everybody.
Hello, Carolina.
Let's continue with our next session. Our next guest is Thomas, and I will quickly share the slides, and you may start.
Thank you very much. Thank you for having me. It's very nice meeting. I work as a postdoctoral researcher fellow in the Aalto University in Risto Ilmoniemi's group, and I've been doing quite some time already, like TMS-ET data analysis and developed methods for that purpose. And today I'm going to talk about that a little bit. Okay, now it doesn't. What should I click?
To the right, basically. Like this? Yeah.
Okay.
Okay.
Okay, great. So I will already tell the two take-home messages. The first one is that there are a bunch of challenges, signal and quality challenges in combined TMS-ET from various factors. However, I would want to kind of promote the idea that by using the or understanding the underlying physics and physiology, we can suppress effectively some of these artifacts. That's a small promotion. We just published this kind of a handbook review of these methods that I'm going to present today. So there will be much more thorough explanation about the methods, how the theoretical background, and also especially all sorts of practical tips how you could use them as effectively as possible in your data analysis. So here, let's look at some artifacts at first. So this is from the Rogash paper from 2017, and we can see there are some examples of possible problems. You can have TMS-evoked muscle artifacts, you can have electrical movement. On the next slide, we have blinks, eye movements, you can have persistent muscle activity, or some electrodes might be noisy, maybe there's a bad connection. And for the purpose of this talk, I think what you should really concentrate on is the topographical patterns of these artifacts, and keep in mind how those could look like. Now the standard approaches, or maybe the most common approaches still in the TMS-ET field or ET field to tackle these artifacts and disturbances are to use some sort of statistical approaches, some sort of blind source separation methods, which are really data driven. So for instance, independent component analysis is a very popular and common way. How these methods work is that they don't really take that much prior information inside the algorithms, even if we would have some. They are really kind of based on the idea that you feed in the data, and then you hope that these components will fit the statistical assumptions. So I think that is kind of the main theoretical limitations, or at least my concern, is that to what extent can the TMS-evoked components, signal components, be assumed to be independent? Because we are really looking at time or event-related data here. So it is kind of hard to understand how they could be statistically independent when you see a muscle artifact, then that gives you direct information that there probably should be also transcranial evoked activity as well, because there has been a pulse. So I think these are kind of the main weaknesses. The other, of course, common approaches are to do some sort of frequency-based filtering, like Fourier filtering. But there the problem is that quite often, almost more often than not, the artifacts can have really overlapping frequency spectra with the neuronal responses. So in that case, of course, it doesn't really work that well. So I will present you a couple of methods that are based on modeling the cortical reactions and leveraging that information into suppressing these artifacts. So we of course know from the modeling and theoretical electromagnetics that TMS induces a strong electric field on the cortex, and it depolarizes some of the neuronal populations sufficiently to cause action potentials. And now, if we have enough action potentials in a neuronal population that can create synchronous postsynaptic currents that are kind of go into the same direction spatially, then those postsynaptic currents can create large enough signal that we can detect in EEG. And what is especially important is that the cortical sources the return currents that they create, they have to travel through the well-conducting brain, poorly conducting skull, and then again well-conducting scalp. And from these features, we can expect that any topographies that should be coming from the cortical sources should have rather low spatial frequencies, or they should be quite smeared. So here in this example image, we have modeled the topographies from this source using different assumptions for the head conductivity. And really the B panel, you don't have to care about that because there we, as you know, skull. But you can see in all the other C, D, and E, if we add even quite moderate contrast between the skull and the other tissues, you immediately see this effect that the topography start to smear considerably and the spatial frequencies go down. Before going into the actual algorithms, I want to raise one more point about the EEG, how we view EEG. So I think the conventional way to view EEG is to think about it as time courses or kind of wiggly lines measured by the channels. And I really think that this type of thinking maybe promotes filtering in the time domain or frequency domain. But I think you can also think about EEG, even streaming EEG from slightly another angle, and that is kind of seeing it as a stream of snapshots of the voltage patterns. So even when we have like continuous long EEG data, it is nothing more than changes in the overall voltage patterns on the scalp. And if we have some knowledge how we could filter these snapshots in the spatial domain, maybe we could use that to remove the artifact and noise and uncover the underlying neuronal responses. Here you can see that these topographies are probably quite noisy. They are just from raw data that I took here as an example. And later on we will see how one of the algorithms, what it will reveal under these spatial patterns. So now I'd like to go to the first algorithm that we call sound. And sound was developed for kind of a general noise rejection, noise suppression. It works great for MEG and EEG in general, but of course for TMS-EG it's quite useful because TMS-EG is especially prone for having a lot of noise and artifacts. So I will not go into too much into detail how this algorithm works, at least in this first 15 minutes, but if you have questions then we can go through it more thoroughly. But really the idea is that we are taking one channel at the time, and then we are comparing the measurement in that channel to the prediction that you would get from all the other channels. The prediction that you get, that is based on doing an inverse estimation from the other channels and then modeling that inverse estimate in that studied channel. And if the predicted signal based on the other channels and the actual measurement in that channel, if they differentiate a lot, then we consider that channel to be more noisy. And we do this in a kind of a smart iterative way to estimate the noise levels of all the channels. And as an end result, we have a very simple spatial filter. So we have just a linear spatial filter for our data y that we can operate from the left. And that basically what this spatial filter does is to do exactly what I said a couple of slides back. So filter those snapshots of topographies. So here there is some example data from, I think the right primary motor cortex was stimulated for this participant. So you can see this is the data here is in pretty raw format still. There is some basic baseline correction and maybe some worst trials have been removed, but overall it's really raw. And then when you run the sound algorithm and filter spatially, you get this. So you already are able to uncover a lot of topographical patterns that seem based on their shape and characteristics. It would be unbelievable that these come actually from the cortex. There is still some muscle artifact left. The reason is that the muscle artifacts, they have also like some correlations across the channels that you cannot separate that easily from genuine cortical responses. But this is a good kind of a pre-processing step. And if you need to, you can do further steps to suppress the muscle artifacts further. And here going back to this one slide, we had these broad topographies, and again, filtering them with the sound-based spatial filter. This is what you actually get underneath. I have to say this is rather easy case for the sound because it's basically corrupted by these few isolated bad channels, but it shows that it works in this case very well. Then I already mentioned the TMS evoked muscle artifacts. So we have developed a couple of years back a method that is closely related to sound. And the easiest way how you would maybe hope to remove the muscle artifacts would be to only remove the channels where those muscle artifacts are. That would be the easiest thing, right? The problem, of course, is that muscle artifacts are seen by multiple channels at the same time, so that doesn't make sense. But what you can actually do, you can actually imagine that maybe there would be a virtual channel in this channel space that would be as sensitive to muscle artifacts as possible, and you remove that one. You can think about this virtual channel also as a topography or a dimension of your data. And that's the idea. So we try to estimate the topography of the muscle artifact that we can project out from the data, but in a way the mathematical operation is completely analogous of removing 1 or 2 or 3 channels. It is just kind of arbitrary dimensions. And the trick that we do to estimate these topographies is the following. So we actually first high-pass filter our data because we know that the neuronal EEG signals are present mostly below 100 Hz. And that way what we get left is the pretty much only muscle artifacts. And we'll take some of the biggest muscle artifact components and those present the topographies or the signal space dimensions that best portray the muscle artifact. The problem is that, that when you do this kind of a funny mathematical operation, the signal looks often quite funny at first, seen on this right upper corner. The reason is that we are accustomed to seeing our EEG on these physical locations of electrodes. And now when you remove these kind of arbitrary virtual electrodes from your data, none of the rows of your data anymore correspond to actual physical locations. And that's why we, as a solution, we introduce this source-informed reconstruction step. And the idea is very simple. So even though we have done this kind of a detrimental operation, we know exactly what we have done to our data. So it's a simple linear operation to our data, and we can actually take it into account in the source estimate. So we can estimate the sources that would produce the artifact-free signal. And once we have the source estimates, we can calculate a model how they would look like in the original signal space. And that's the idea of the SSP-SIR combined method. Here is some example data from the original publication. So you can see the red data is the artifactual data before the SSP-SIR, and the black ones are the activity after the cleaning. And here this first row shows the original topographies, and then the bottom row shows the topographies after the removal. And oftentimes it's difficult to get the ground truth, like how can you trust whether the cleaning has been successful? At least in this case, what we did then was that we looked at from the navigation, the stimulation location. Well, you can see here the arrow. And then we placed a dipole portraying post-synaptic current, initial post-synaptic current at the stimulation location. And actually the uncovered topography and the model topography C versus D, it actually corresponded quite nicely. So I think something like this, at least in some research questions, could be a way to control to which extent is your artifact removal successful. And then the last part of this talk, I want to talk a little bit about how to further quantify the effects that you do on your data. So oftentimes people are really worried about how much do you jeopardize the signals of interest, which is of course natural, and it's a super important question. And I think what is the strength of these type of spatial filtering methods is that you can, okay, they do compromise the signals of interest, but at least it's quite easy to objectively quantify the effects. So what you can do is that you can model all the possible cortical sources cortical post-synaptic sources and calculate their topographies using the modeling tools. They are quite abundant nowadays in different toolboxes. And then you can construct your lead field matrix. If you are not that familiar with the lead field matrix, it's in the end of the day, it's nothing more than just a collection of those topographies as the columns. So basically, lead field is a description of all the possible post-synaptic sources you could expect from the cortex. And now once you have your lead field matrix, what you can do is that you can calculate the spatial filter from your data, this W filter, whether it's a sound filter or SSP SERV filter. And now what you can do is that you can apply it to your lead field matrix and ask the question that, okay, provided that we were stimulating the red arrow location and we had to do this type of cleaning, what sources are mostly compromised by this operation? And we can see, for instance, in this case, stimulating the right primary motor cortex, is that we do compromise the sources quite a bit from that stimulated hemisphere. The reason might be that the muscle artifacts have been quite big. But the good news is that, for instance, let's say that your research question would be particularly interested in the transcallosal connectivity from right to left primary motor cortex. We can actually quantify and see that those sources are not affected that much. So even though we don't have necessarily a ground truth, strictly speaking, we can quantify quite nicely the effects like this. And okay, so this was basically the 15 minutes, maybe a little bit longer version of the actual signal analysis. But then I was given the permission to talk a little bit in the discussion about this initiative that we have had for a global collaboration between TMS-EEG groups. So kind of the bridge from this talk about data analysis to this initiative, I want to mention this paper that we had last year with Giacomo Bertazzoli and others, where we basically compared the different popular pre-processing pipelines and the outcomes that you might get for your TEPs. I think the problem is that nowadays groups are using so complicated pipelines that it's very difficult to get your finger on the actual interaction effects between these methods. And that might be the reason that is causing these differences. But it would be really important to understand where this is coming from. So with this group of researchers, including, for instance, Marta Portoletto, Domenica Veniero, Julio César Pavón, Agnese here, and some others, we are now introducing these teams for TMS-EEG. We call it TAPE, at least Agnese and I. And the idea is that we would get together as a community and do large-scale cohorts for studies to see where these differences and replicability issues are coming from. So in the first study that we are suggesting, to which we have written now description that you should go and check from the TAPE website, we are going to look at the reliability of different metrics when stimulating the primary motor cortex. And what we need is both experimenters who are willing to collect the data in their group, but also data analysts who are willing to do the data analysis, because this is kind of a two-sided problem. We have maybe variabilities on the experimental side, but we might also have variabilities from the data analysis side. So have a look at the requirements at the website. I have them here just kind of a food for thought. You don't have to go through them at detail, but the important aspect is to know that there are some requirements. But if you are worried that you would not meet some of these requirements, but you would still like to participate, please be really don't hesitate to contact us, and let's see whether we can arrange something. And even though we have these requirements, we also have to take into account that the idea is to come up with a registered report. So we will present to the reviewers an idea of how this big scale study will go on. And of course, it's possible that the reviewers will also give their comments. So we cannot even say that this is the final version of the experimental setup. So also from that perspective, it really makes sense to contact us, even if you couldn't meet all the requirements. If you want to participate in the data acquisition, it's a maybe a little bit bigger task for the group. So that's why we are allowing more authors to participate to be published paper. Wasn't it 4 of 3? Okay, 3. Yes. So 3 if you are doing the experimental side. If you want to do data analysis, then only one author per group, because you don't necessarily need so many researchers. You can see here the tentative timeline. So now we are collecting the groups and participants who would like to contribute, and then in the beginning of next year we will start common discussions about the first project, and start really like writing the ethics and forming the registered report. Yeah, we encourage you to participate. Yeah, thank you. I think now you should definitely feel some.